Hello everybody and welcome to this our second FlameSpec webinar. Today I will be talking for around 40 to 45 minutes about our FlameSpec IIIR flame detector and how it provides new levels of performance in optical hydrocarbon flame detection. In a later webinar we will specifically discuss how our flame detector family addresses the needs of the energy transition market by looking more closely at applications for hydrogen, ammonia, and battery storage. For now, let me introduce the agenda for this session. Today, we will present a short overview of Fire and Gas Detection Technologies, Inc., and how far we have developed since being founded. We will then summarize flame detection technologies and the factors that affect detection and false alarm immunity. This was very much covered in the first webinar. The main presentation will focus on our FlameSpec IIIR hydrocarbon flame detector. We will explain some of the detail behind the design and explain what makes it different. We will finish with a few typical examples of applications and a summary. So without further ado, let me introduce Fire and Gas Detection Technologies, Inc. Many of you might know that our company was founded in 2017 by a group of highly experienced people who left Spectrex following its acquisition in 2015 by Emerson. Fire and Gas Detection Technologies was established with the aim to offer faster optical detection products with market-leading false alarm immunity and first-class customer service. Last summer, we moved from our unit in Brea, California, into a much larger primary manufacturing facility in Anaheim. Here, we have capacity to produce more than 12,000 detectors per year, although I should state that this is not the ceiling for manufacture at this facility. From Anaheim, we operate all sales, marketing, training, and technical support activities. The factory is naturally ISO 9001 certified, as all of our products carry hazardous area approval and performance approvals. Let's look a little bit more closely at our timeline since being founded. You will see that up until 2019, the primary focus of our company was to develop a world-class product line of optical flame detectors. In 2019, we saw the finalization of some major certifications. These include Factory Mutual, ICX, and ATEX. In 2020, the focus turned to global distribution channels, partnerships, and key end-user approvals. In 2021, we continued to expand our distribution network, increase market awareness, and of course, add more approvals. We've also started development of an open path gas detector platform, and we'll present more on this at a later date. And so today we have two flame detector product lines matching technology with fire risk and application considerations. The technologies cover UVIR for hydrocarbon, metal, and inorganic fires, IIIR for hydrogen, silane, and some other special applications, and of course IIIR for visible and invisible hydrocarbon fires. The two product lines were developed to have the same flame detection and fire alarm integration capabilities. The main difference between the two lines is with the video capability of our HD detectors. We will learn more about this in this presentation. Right now, we will pause to quickly review what affects flame detector response. Our starting point is always what is going to burn. A large luminous smoky flame like crude oil, or a low energy near invisible flame like methanol burn very differently. Whichever it is, we must ensure the flame detection technology selected is able to respond to the fuel burning. Detector sensitivity and distance from the fire are very much linked factors. We then need to consider the detector field of view in both the horizontal and vertical planes. As a side comment, you might find it interesting to learn that a field of view greater than 90 degrees in the horizontal axis does not always equate to better performance. I'll leave you with that thought for now, as we will discuss this point further in the presentation. And another point to consider is the environment in which the detector is installed. For example, the demands of a detector in an acoustic enclosure of a gas turbine is very different to the challenges posed by the depths of winter in Canada or Kazakhstan. And last but not least, we must turn and consider false alarm sources. Flare stacks are friendly fires. The challenge is that no flame detector can tell the difference between a hazardous fire or a friendly one. Care and attention with the installation, linked with mechanical blinkers and sensitivity reduction, can normally help minimize false alarms. Hot objects, as we will see in this presentation, can cause issues for some flame detectors. The main recourse here is to reduce sensitivity. Sunlight and sunlight reflections can be an issue for some flame detectors. Mechanical interchanges may help where this is an issue. When hot work is being conducted in close proximity to a detector, it is normal to isolate the alarm outputs. The main historical issue relates to arc welding and UV detectors, although activities where heat is produced, such as grinding and cutting, may be an issue for some IR flame detectors. And finally, hot CO2 or carbon dioxide emissions can cause some multispectrum IR detectors to alarm if they are mounted in close proximity to the source. This issue can be resolved by relocating the detector, or if this is not an option, other solutions may be available. The challenges posed by the fire risk, application and installation and presence of false alarm is a complex one. So when we take these points into consider, we must always ask, is there a perfect flame detector? And as always, the answer is no. All flame detectors have strengths and limitations. Therefore, when selecting a device, it is important to use the most appropriate technology for the application. This is, of course, why we have a range of products and technologies that match the challenges of the installation with the detection performance needed. In this webinar, we will be focusing on the FlameSpec IIIR hydrocarbon flame detector. So, what have we developed? Well, we developed a detector that in a single unit responds to explosions, fast fires, slow evolving fires, small fires, and big fires. The detectors work indoors or outside over an extremely wide operating temperature range. The detectors have best-in-class response to a broad range of fires and outstanding false alarm immunity, all of which is approved by Factory Mutual. In a single unit, we deliver as standard fire and fault volt-free contacts, a 3-wire 4 to 20 milliamp, both current sink and current source, an isolated 4-wire 4 to 20 milliamp, and an RS485 port utilizing Modbus RTU. We also include heated optics, adjustable sensitivity and time delays, all again as standard. What is more, all of our detectors are delivered with a 5 years warranty. As mentioned earlier, our HD units provide a live video feed and high-speed recording of events, 1 minute before the alarm and up to 3 minutes after it. I'm sure you now want to know something of the detail of what we've actually done. So, with a mature technology, it's unlikely that dramatic improvements in detector performance would occur due to changes in any one area. In the following slides, you will see that subtle incremental changes based on years of product knowledge have culminated with the development of the FlameSpec IIIR. The first area we will focus on is the wavelength and filter selection. This was supported by live fire tests where we captured both data and video in color and near infrared from fires. The next step sees us focus on the optomechanical design, how we heat the optics and tightly control light entering the sensors. Finally, we will mention PCB construction, the termination chamber, and flexible options where we provide for interfacing to panels and control system. But first, we need you to do a little bit of work. So we have a quick poll. You will see a window will open up on your screen, and in it we will be asking a question. The question is, which flame spec enhancement do you consider adds the most value to the end user? There's no wrong answer. You can select as many as you want. I will open the poll now. You've got about 20 seconds left.
I think you have a very clear leader there, Elliot.
It is very, very clear.
An interesting second place as well. Just.
There you are. So I will show the poll. Ian, do you just want to quickly talk about it?
Yeah, so thanks everybody for voting there. So we have 27% went for speed of response. 22% looked at sensitivity or detection range. 31% for the integration flexibility, so all the functionality in one box. But the majority chose, and this is 56% of you chose false alarm immunity. So yeah, interesting survey. As Elliot said, there was no wrong or right answer, and the answers can be obviously varied depending on your experience, whether you're a user or whether you're a seller of flame detection or whether you're an integrator of flame detection devices. So thanks very much for that information. As I said, false alarm immunity, 56% was nearly double the other answers. So appreciate your input there. Thank you.
Excellent. Thank you very much for that. And just so you know, I now have to open the next poll, which will be coming up later in the presentation. So, okay. So moving on, what we now need to focus on is the wavelength and filter selection. It is widely known that hydrocarbon fires generate a plume of hot carbon dioxide, and that most IIIR flame detectors use this key feature to detect flames. Our fire band wavelength is centered around 4.5 microns, and we use two adjacent guard band wavelengths, one at 4 and one at 5 microns. These wavelengths help improve the false alarm immunity of the flame detector. One point I should highlight is that there is no overlaps of the wavelengths we use. This is important as it means the information we're receiving from each sensor is uncluttered. A good analogy is to think of the sensor filter combination as a single pixel camera. The colors that we receive from these cameras are vibrant and sharply defined, and they are completely uncluttered. This means that the analysis of thresholds, signal ratios, and correlations can be conducted more quickly. This, coupled with enhanced signal flicker frequency analysis, improves positive fire detection and false alarm immunity. Naturally, the algorithms we employ and develop are key to the detector performance. We will now look at that now. Our new development has allowed us to capture data and video from a huge range of fire and non-fire events. The fire events would cover visible and invisible hydrocarbon fires, those that were clean burning and those that were dirty or smoky over a variety of distances from very short to very long, by which we mean up to about 100 meters or nearly 400 feet. Non-fire events were tested at very short distances, as typically these were less of an issue the further removed from the detector you were. Typically, we examined arc welding, electrical arcs, modulated and unmodulated objects, as well as direct and indirect sunlight. The information we captured directly related to the factors we used to differentiate fire from false alarms. Inside each FlameSpec IIIR, there are over 50 factors that are monitored as part of the detection and false alarm rejection algorithms. Algorithm revisions are validated against the vast library of data for fire and non-fire events to ensure changes only have a positive performance impact. In the next 2 slides, we will present a brief glimpse of the 3 signals the FlameSpec IIIR uses. In the first video, you will see the recorded feed from our internal development tool. On the left-hand side of the video, you will see a graph displaying the output from each of the 3 filtered IR sensors. On the right-hand side, we're showing the live video feed from the FlameSpec IIIR HD detector. The first video shows the sensors will not respond where air in front of the detector is modulated. And as you see, there are almost no signals at all. We then introduce a simple heat source close to the detector and modulate it. This simple example might represent a detector looking at a hot vessel, heat exchanger, or a pump on a facility. If a group of technicians were to walk between the hot object and the detector, a chopping motion of hot, cold would be seen. Watch as the 3 signals are generated, 1 per filtered IR sensor. Notice how close the correlation or tracking is between the 3 sensors. You look here. In the next video, we introduce a small flame in the presence of the unmodulated heat source. The blue line in the graph is the output from our 4.5 micron sensor. This will show a strong response to the flame, whereas the other wavelengths have negligible response. The second video on this slide demonstrates a much harder challenge for the detector, as we are actively trying to confuse it by mixing a modulated heat and flame source at the same time. As with the modulated heat source video on the previous slide, the detector could be looking at a hot vessel, heat exchanger, or pump when the chopping motion of hot, cold would be seen. This time, watch as the 3 signals are generated due to the modulation, and then what happens when the flame is introduced. You will see that the correlation of the guard band wavelengths remains closely matched, and that the response at 4.5 microns is very strong. The detector correctly identifies that a flame is present. One other point just to note was that the traces were all continuous, so I promise you there's no smoke or mirrors or video editing going on there. Next, we need to look at our enhanced optomechanical design. The FlameSpec fascia gives it a very distinctive look and feel. Unlike some competing products, we have no need to use sunshades to stop water dripping into the detector optics. This is because we have a brow that forms part of the stainless steel casting. The 3 IR sensors sit behind a heated sapphire window. The FlameSpec design uses a heating element in direct contact with the window, as this is a more efficient way of heating the optical surface than using an array of resistors mounted more remotely. As a result, we have lower power consumption than many competing devices. Finally, each sensor sits in a precision machined pocket where incident light is restricted to 45 degrees either side of the central axis, thereby giving a 90-degree horizontal field of view. It is important to stress that each sensor, rather than the detector as a whole, has exactly the same field of view. Let us review this in more detail. Looking at the FlameSpec design, we can see each of the 3 sensors is tucked behind a bandpass filter, selected to the wavelength of interest, either 4, 4.5 or 5 microns respectively. As mentioned previously, this precision machined pocket restricts light to 45 degrees either side of the midpoint, thereby giving each sensor a horizontal field of view of 90 degrees. If we consider an alternative semi-controlled design, the detector may claim to have a field of view of 90 degrees, and it is clear that light entering the extreme left of the sensor onto the left is restricted to 45 degrees, but light to the right-hand side of the center point is unrestricted. I'm sure some of you are asking, why is this important? Well, the challenge faced by this design is called blue shift. In basic terms, the transmission properties of a bandpass filter changes depending on the angle of incoming radiation. When infrared energy enters from angles greater than 45 degrees, the sensors see different wavelengths. This unwanted additional data can distort the ratio and correlation of the signals received, which may impact the ability of the algorithms to correctly differentiate fire from false alarm, meaning that the device performance may be compromised. Moving on, let's have a quick look at our design. Pictorially, this slide represents the journey we've been through with our FlameSpec III-IR development. We started with a blank piece of paper and a mature technology. We knew that dramatic improvements in detector performance would be unlikely due to changes in any one area. We therefore started to capture data and video of fire and non-fire events and developed algorithms from scratch using this data as input. We've already seen how our optomechanical design tightly controls light entering the sensors and why this is important. The integral visor simply stops water from dripping into the optics, which are heated to prevent ice or condensation. The PCBs are tropicalized and the termination compartment is integral to the detector but segregated, which usually makes for a less problematic installation. We also have possibly the most complete range of outputs that can be purchased in a single part number. A 3-wire 4-to-20 current sink and current source, as well as the isolated 4-to-20 milliamp. We have fire and volt-free contacts and an RS485 port using Modbus RTU. But we're not finished there. We also offer detection to explosions. Our ultra-fast detection mode is available in all FlameSpec detectors and uses an independent and parallel detection path to our standard flame detection algorithms. Ultra-fast detection does not affect the speed, sensitivity, or any other aspect of the standard detection mode. Similarly, the sensitivity and alarm delay settings do not have any impact on ultra-fast detection. The ultra-fast response for our IIIR detectors is 40 milliseconds to fireballs and explosions at short distances. Here's an example. Keep an eye on the red lamp, which is positioned here, just to the right of the detector and above the FGD logo. That was in real time. We'll now show it slowed down completely. Okay, now let's explain a bit more about the published data that we have. In the next few slides, we will show in more detail the performance levels we've achieved with our FlameSpec IIIR detectors. To my knowledge, FGD uniquely publishes more FM data in our product data sheets than any other manufacturer. The details published include detection distance and response times to different fuels. We also include the results of immunity to false alarm in both modulated and unmodulated conditions. Let's look at some performance data. Let me explain a little about this slide. The response time shown are the average response per our FM test report. The fire under test is the same. It is the standard 1 square foot or 0.1 meter squared N-heptane fire at each distance. This means as we move further from the detector, the radiant energy it receives reduces. This essentially matches the inverse square law. So if we double the distance from the detector, it can only see a quarter of the energy that it saw at the shorter distance. In order to maintain detection, we manually increase device sensitivity. One interesting point to highlight is at the limits of detection. Looking at the extreme sensitivity to the right-hand side of the slide, you can see this is around 80 meters for this fire type and size. You'll also see that the detector takes longer to decide if a fire is present at 80 compared to 70 meters. This is because the detector runs additional validation checks when the received fire signal is low. Let's now look at some other of our FM data. Here we present performance data extracts of our IIIR and IIIR HD product data sheets. The information shown relates to different fires, including liquids, gases, and solids. The detection distance and average response time is given for the stated fire size and sensitivity. I'll give you a few moments just to scan the data. Whilst you're doing so, I'd like to point out a couple of things. First of all, the response time for the two detector types are broadly similar, but not identical. This is simply due to the experimental setup, as the fires were not conducted simultaneously. As a side comment, we do have some simultaneous fire test examples later in this presentation, where you'll see a much correlation in the speed of response because the detectors will see the same fire. Secondly, it's worth pointing out that the detection distance is not fixed. For example, our IIIR can see beyond 80 meters if you look at the response data for the 2x2 gasoline fire, but the fire must be bigger to do so. Now let's look at the immunity to false alarm data, which you all identified as the single most important factor for end users. It is important to highlight the false alarm tests were conducted with our detectors placed on their maximum sensitivity, which is the extreme setting. That means an 80-meter response to a 1 square foot N-heptane pan fire. Here we compare our immunity to false alarm data with that of a market leader. On the next slides, we will see some more response data, but I think on this slide, the one thing I would particularly like to highlight is the difference in response on the most extreme settings for arc welding. We're typically around the 4-meter mark for a false alarm, whereas a competing product is nearer to 12. Moving on. The information presented on this slide relates to the factory setting of both units. Most manufacturers' default is medium sensitivity, which typically means a 30 meters or about 100 feet to the standard N-heptane test fire. Whilst the list of fuels is shown is not exhaustive, the data presented is FM approved. Generally speaking, I think the data shows the flame spec to have a more uniform response across different hydrocarbons, whilst at the same time giving improved sensitivity and speed of response. The following video gives a head-to-head comparison of market-leading devices. The intention of the video is not to knock the competitors' high-quality products. They respond well and in a timely manner. We're simply wishing to demonstrate the additional speed gains we have achieved. Naturally enough, all the devices are configured the same and have the same 0 time delay settings. A couple of slide backs, I mentioned that we would see some simultaneous fires, and this is an example. Here you see there's a much closer correlation between the speed of response of our detectors. And now I have another quick poll for you. So there's 3 questions to answer just based on some of the information that we've seen. You have approximately a minute to respond. We're just waiting for a couple of respondents to complete the poll. I'm happy to say that you've been paying good attention, so thank you very much for that. So the ultra fast response is 40 milliseconds. That was very well defined. The video outputs are PAL, NTSC, and ONVIF Profile S. That again was answered well, and the factory default setting is medium. So well done. Thank you very much for answering those questions for us. Now, in the video we just saw, you saw a glimpse of our HD detector. And now I would like to just share with you some of the capabilities that we have with that device. So as previously mentioned, our RRR flame detector is also available with an integral CCTV camera. The live camera feed delivers high definition quality video output using ONVIF Profile S format. For retrofit applications, we also have PAL and NTSC. The video element of our detector helps elevate on-site safety by providing clear video stream of the area being protected. In the unlikely event of an incident, informed decisions can be taken more quickly, and first responders can be appraised of the situation and directed more appropriately. As an additional feature, fire events are recorded at high speed both before and after an incident. As standard, the video recording before detection is 1 minute, and after detection, an additional 3 minutes can be added. This video contains time and date stamped information, which can be used as part of a post-incident investigation. The next video clip has been cut down from the full recording. At the top of the screen, you will see the time and date stamped information. This can naturally be synchronized to the local clock. There's the time and date stamped information, and you'll see the detector responded. The event video feed can be extracted using a web browser, the ONVIF device manager, or our own FGD communicator. By way of a quick introduction, here is our FGD communicator. This software is required if changes are needed to the configuration of the detector when shipped from the factory. The main features of the software are the ability to communicate using Modbus over an RS-485 port. Parameters such as sensitivity, the ultra-fast response, the delay time, latching of relays or the standard 4 to 20 milliamp signal, the selection of the heater, and also whether you want video on or off, or whether you want to select PAL or NTSC video, are all available through a password protected environment. The software can also communicate with the IIIR HD via an internet connection that allows live streaming of the video and the ability to retrieve event recordings. In the next few slides, we will cover detector testing, approvals, and accessories. Testing can be conducted externally using one of our ATEX approved flame simulator kits or via a manual built-in test. If testing is conducted using the test torch, the detector outputs are activated and a complete system check is performed. The manual built-in test has two options. One that simply tests the detector internals and the cleanliness of the optics, and the other that performs a full loop test in much the same way as the test torch. The automatic built-in test initiates every 15 minutes and is used to verify electronic circuitry, sensors, and window cleanliness. It's important to note that if a fire is detected and the unit is in built fault, the fire will override the fault signal. This slide denotes the approvals we already have in place, and I will mention some of the additional ones we're working towards. You will see that the core hazardous area approvals of ATEX, ICX, FM, EAC, and PESO are already in place. We also have performance approvals to FM 3260 and EN 54 Part 10. What is more, our FlameSpec IIIR detectors have been approved by DNVGL to the very rigorous MED, the Marine Equipment Directive. You will no doubt have noticed that our SIL capability is by FMEDA at the present time. We are working to obtain full certification before the end of the year. And finally, we have started work to obtain VDS and UKCA approval. Moving on, just a few slides to talk about our accessories. The tilt mount brackets offers true versatility for installation, and it has adjustment in both horizontal and vertical axis. What is more, the fixing centers of the base plate are identical to some of the market leading brands, meaning retrofits are very straightforward. The pole kits can be mounted with a 2 or 3 inch pole as standard, and others are available on request. If customers insist, we can also supply sunshades as well. And the latest addition to our range is an air shield. This item can be supplied either for the standard or HD detectors, and the air shield uses compressed air to flow an air curtain across the detector window, thereby preventing accumulation of dirt on the detector or the camera window. Now looking at some applications, we're able to satisfy a wide range from the most obvious like offshore marine, LNG, tank farms and refineries, things also like large vehicle protection, loading racks and compressors, to the less obvious, aircraft hangars, waste transfer stations, biomass facilities, recycling centers, waste to energy plants, battery storage, spray paint booths and others. And our HD units are ideal when remote monitoring of site or process is needed. Applications like normally unattended facilities, gas plant, remote tank farms or pipeline booster stations spring to mind for the use of the video. We're now coming towards the end of our presentation. I'd therefore like to summarize our development in this our webinar entitled Delivering New Performance Levels in Optical Hydrocarbon Flame Detection. By way of a summary, I'd like to mention what we discussed. We had a short overview of fire and gas detection technologies and how we developed since being founded. We then summarized flame detection technologies and what affects detection and false alarm immunity. The main focus of this presentation has, of course, been our FlameSpec IIIR hydrocarbon flame detectors. We discussed how we started from a blank piece of paper and a mature technology. We knew that dramatic improvements in detector performance would be unlikely due to changes in any one area. We therefore started capturing data and video of fire and non-fire events and developed algorithms from scratch using this data as input. We saw how our optomechanical design tightly controls light entering the sensors and why this is important. The integral visor simply stops water dripping into the optics, which are heated to prevent icing or condensation. The PCBs are tropicalized and the termination compartment is integral to the detector but segregated, which, as mentioned before, usually makes for a less problematic installation. We also saw that our FlameSpec IIIR detector has a more uniform response to different hydrocarbons, whilst at the same time giving improved sensitivity and speed of response, all of which is independently approved by Factory Mutual. We also have possibly the most complete range of outputs that can be purchased in a single part number from any flame detector manufacturer. As previously mentioned, 3-wire 4 to 20 milliamp sync source, isolated 4 to 20, fire and fault volt-free contacts, an RS485 port utilizing Modbus RTU. I firmly believe that our FlameSpec IIIR has truly raised the bar regarding flame detection performance and what customers should expect from manufacturers. Finally, I have one more head-to-head comparison of market-leading devices, this time to a gaseous fire. The intention again of this video is not to knock the detectors of the competitors. They are high quality and they respond in a timely manner. We're simply wanting to demonstrate the additional speed gains that we have achieved. Naturally enough, all the detectors are configured in the same way. And as before, I'd just like to mention how closely our detectors actually match one another. And so, without further ado, we've reached the end of the presentation, and I'd like to thank you very much for attending. And Ian, are there any questions that we need to answer?
Yeah, thanks, Elliot. Yes, yeah, there's a few actually. We have some on the chat, which I'll go to first. I've sent some people the link to the YouTube video from the first presentation. And the first question on the chat, which I did reply to everybody, but does an air shield lower the view angle of the detector? And if so, by how much?
Okay.
I'll let you answer that verbally.
It's a very good question. Actually, we've designed the air shield so it has no impact in either the horizontal or vertical field of view of the detector. So the performance of the device is completely unaffected from what is published on the data sheets.
Okay, thanks. And Rajan Prakash asked when to use UVIR and IIIR detectors. Can you elaborate? I think that's probably the topic of another webinar, actually. It's not a very simple question to answer, but have you got any basic advice?
So pretty much, if in general a hydrocarbon flame detector can actually respond to the fire, my preference is to use it, providing it's suitable for the application. If it was an extremely hot application with a lot of vibrating surfaces around, it may be that one would more tend to move towards a UV-based detector and not even necessarily a UVIR than a IIIR, but it really does depend exactly on the application. I think the one thing that's important to highlight is, generally speaking, the UVIR can detect a broader range of fires, but we are now starting to move away from hydrocarbon fires, which is the subject for today. Certainly in our next presentation, which will be about energy transition, we will highlight some real advantages where the UVIR detector can actually be an advantage. So I think that the comment is wait till next time, and we'll definitely fill you in on more details then.
Okay, and another question in the chat from Jean-Marie. Jean-Marie, you had a couple of questions. I'm not quite sure, I don't understand. Optical checking cover only 1IR detector. I'm not quite sure what that is.
I think I understand what Jean-Marie is saying. So there's at least one manufacturer on the market that actually would do a through lens optical check on each of their 3 individual sensors, whereas most of the manufacturers and actually a lot of the end users are very happy that they understand that optical contamination does, broadly speaking, land on a detector in very much the same way. So if one of the sensors is becoming contaminated, then you know that the other ones are, which is why we typically just employ a single one. There's another point to it, and that is the main manufacturer that uses 3 also is using part of the information from each of those 3 sensors as part of the main fire detection algorithm, whereas we principally are using the 4.5 microns. So for fire detection capability, the sensor that we cover with the optical check is the most important one.
Okay, thank you, thanks. And then last one from Jean-Marie is, can we use the IIIR H2 for hydrocarbons?
You can for some, so it is able to detect methanol, but it is nowhere near as strong in performance as the standard IIIR detector. So we would have to look at each of the individual fuels that's going to burn, because the sensitivity to a standard hydrocarbon fire is nowhere near the same. So again, it would come back to the application, understanding the fuels that are going to burn, and then make sure we are matching the right technology to the application itself.
Okay, and I think just to respond to your question, Jean-Marie, we'll provide you with a lot more information for hydrogen after the webinar. Okay, I'll take a note of the questions. Rajan again, fire due to hydrocarbon gases or gasoline in turbine compartments. Can we use IR3 sensors to capture fire and eliminate present heat detectors?
So the answer is it is possible, but what we actually have to do is use a much lower sensitivity detector, because, well, the detection distances are nowhere near the same anyway. So we would use a modified version sensitivity wise for the inside of an acoustic enclosure. Typically, we're probably going to be down in a detection distance on axis of about 7.5 meters, which for a turbine enclosure is going to be more than enough.
Okay, thank you, thanks. And a question from Singapore, from Skippy. Do you think field of view restrictors may be required, or are the algorithms significantly improved if one cannot avoid certain known sources? Understanding placement is the key factor. So it's a good question there about interferences and how our algorithms are managing those.
I think it would simply depend on what we're talking about as the false alarm source. If the detector has an absolute direct view of a flare, and depending on the size of the flare, it's going to be able to see it. So there, I would definitely be seeking some sort of mechanical change to the installation, whether it be the use of a blinker or whether it be to actually relocate the detector. One would actually have to look at the individual example itself. Hopefully the person who designed the fire and gas system would actually have worked out where the flare was and tried to position the detector accordingly in the first place. But that's not always the case.
Yeah. Do you see any improvements in the future which can manage those?
There may well be some that we'll talk about a bit later in the year, but that's definitely the subject for another FlameSpec webinar.
Okay, thanks, Elliot. And a question here from Vladimir Tomic. Are there any software that is certified in 2D or 3D with which we could work on projects and predict how many detectors we need for some space? I think it's a good question for the next webinar, right?
Okay, so that sounds like Vladimir is wanting mapping software. So the bit that I'm not clear about is the comment about certified. So there are definitely software tools that are available on the market where you are able to model our field of view in 2D or 3D for any given space or application. They are validated by the manufacturers of the software. I don't know how they would be certified, but Ian, I mean, that's a very interesting plug, so that as part of our last webinar, we did send out a survey, and we will do the same again after this particular presentation. The survey is totally anonymous, but we do like to get feedback. And one of the things that people wanted to get a feeling for was fire and gas mapping. So we have an independent company that's going to come along and talk about fire and gas mapping at the next webinar, which is on the 24th of June.
Okay, thanks. And Patrick Vieira, one of my favorite footballers, is what you recommend for flame mapping. And I think, Patrick, stay online and attend the next webinar that we'll be doing in June. So Ian, thanks for patiently waiting for your question. So Ian's question is on the field of view. On the data sheet, you mentioned the field of view vertical 75, 90%, 90 degrees horizontal. How is this possible when the front is machined to 45 degrees? Does this mean you have a field of view of 90 degrees all round?
Okay, I'm sorry that I wasn't more clear in their presentation. So the 45 degrees is either side of the central point. So it's 45 degrees to the left and 45 degrees to the right. So therefore the horizontal field of view is 90 degrees. And actually in the vertical plane, it's actually 45 degrees below the central point and it's 30 degrees above, which is restricted by the little reflector that we use for the through lens optical check.
Ah, right. Okay, as you can see on the, actually, it's a very so there you can see that on the screen.
Yeah.
Which illustrates that. Thanks, Ian. That was a good question. Thank you, because it's not one that I'd had before either. A question from Gary. What detector would you suggest for conveyors in an energy from waste plant where the type of waste is unknown? General house waste, for example.
It's going to be an organic material, so it will be a triple IR flame detector without question. However, it needs to be correctly located, probably with an air shield, and we would need to consider the speed of response that was needed and how it's going to interface with the control system.
Okay, so if you have organic waste?
Yeah, it's a standard triple IR hydrocarbon.
Yeah, okay. And what about general house waste?
But that's exactly the same.
Exactly the same. Okay, yeah. Thanks. So triple IR on that one, Gary. Thanks for the question. And Marek, some good questions here, by the way, everybody. Thank you. From what I've heard, fog might be problematic because it can act as a bandpass filter with different response to different mid-IR wavelengths. Did you experience false alarms in foggy atmosphere with constant IR sources present?
I think that that is probably something that is more focused towards open path gas detection than flame detection. So the fog itself should not have any material impact on the ability of the detector to respond. Typically for applications, we would be looking at path lengths, or I shouldn't say path lengths, detection distances of about 30 meters. And you won't typically be having fog having any real impact on a fire that's burning at 30 meters. Even at a longer distance, it would have almost no material difference at all. But I think that's mainly focused at open path, and we will talk about that later in the year as well.
Yeah. So energy radiation from the fire is either not affected or less affected by fog in the wavelengths that we're looking at, right? Okay.
Yeah, it will burn the fog off as well.
Yeah, it's true.
A little bit.
Yeah. And a question from Jose: what does FGD use as active material in their sensors for detection? Well, that sounds like a.
I think I would have to ask others. I don't know the answer to that off the top of my head, so we'll take that one away and give feedback.
All right, I think, but one of the points I think you raised in the topic was the sensors are proprietary. They are.
Sorry, I didn't specifically mention that. They're certainly built to a dedicated part number that only we purchase, and they are all tested fully over the entire temperature range that we cycle over.
Okay, thanks.
So there's a lot of work that goes into the IR sensors.
Okay, and we have a final one here. I think I'll just check the chat before I do that. But is from the administrator. Is the IR3 suitable for smoldering flame on a coal conveyor?
That's a good question. The answer is no. And actually, that comes from the previous presentation as well. So no, we have to see a flame. There has to be a fire, no matter how small it is. We do need to see the flicker. It is very important that we see the temporal movement of the flame, as that is an integral part of the detection mechanism, which is why in this presentation, you may recall that we were showing the hot object and then we were modulating it. So if it was just heat, you're not going to see any of that flicker movement and we won't detect it. So it's a very good question. We cannot detect smoldering fires.
And I think that's the reason why many systems incorporate multiple methods of detection, whether you've got heat detection, smoke detection, flame detection, right?
It could well be. And there are ember detectors, for example, that may be suitable for that application as well.
All right, thanks. And kind of a little bit related, how does this detector suppress false alarm from hot exhaust CO2 from engines? Is it tested and fully immune?
So it is not 100% immune. However, it was tested, and actually I asked, when we send out the data, you'll see as part of our FM data, we actually did test it to hot CO2 emissions, and that is FM recorded at 2 meters. Now, we have done some work for some very specialist applications whereby we look at the fuels that are actually going to be burning, and we are able to do some manipulation on the wavelengths that are actually utilized. Towards the end of the year, I would also expect that we will have some alternative strategies to talk to people about. So the way to do it in general is either to move the detector ever so slightly away from the hot CO2 source, or to utilize some of the changes that we're able to employ. But that is very, very application specific when we're going to be manipulating the wavelengths of the detector. But we will have new strategies towards the end of the year.
Okay, this next question I'll sort of add a bit on before I ask you to answer the question, Elliot, but is the product comparisons that we have, I think there's speculation that it's Spectrex or Detronics. I don't think we mentioned necessarily anybody specific, but nothing versus General Motors MSA. We do, in general, have comparisons between our competitors, but I think our focus is not on the competitors. I think you highlighted that the Detronics and the Spectrex units do respond very well. we were focusing on the improvements that we've made and the performance of the FGD flame spec line, as opposed to being negative on any competitors. But Flachon, if I think you could probably take that offline with Flachon.
By all means, I'll do that. It's very, very simple. You know, we can't put all the information up. It's a very limited time slot we're trying to share, and all we're trying to do is actually talk specifically towards the market leaders. And General Monitors is obviously a very, very good brand, but it's not necessarily one of the top 3 products.
Okay, thanks. And we have another one here. Does flame detector sensitivity impact, or is it impacted by black body IR emissions, either background and sunlight?
So it certainly wouldn't have any impact on sunlight, but certainly black body radiation, depending on how intense the heat source was, you wouldn't necessarily be selecting to use an extreme sensitivity. We would probably reduce that, but it depends on the application specifically. It depends on however the design has actually been constructed. And again, we can look at all of that sort of information. So it's very application specific.
Okay, all right, thank you. Yes, so a couple of other comments there. Thanks, John. I think, in fact, we've actually addressed all of the questions that have come up there. So I think we'll call that time on the presentation itself. Would you like to add any closing remarks, Elliot?
I just would like to obviously thank everyone for attending, and simply just to mention that our next webinar will be an introduction to fire and gas mapping. It's going to be presented by Tim Jones. Tim is a principal consultant with RPS. He's been involved with fire and gas mapping for over 10 years, and he's been a process safety consultant for 17 years. And he's also been on the committee for the recently published British Standard on fire and gas mapping. So I think he's a real good expert to have to come along and talk about the subject. And we look forward to sending out the invites to that and welcoming everyone to that presentation as well. The next flame spec webinar that we do, so in other words, specifically about our products, will be looking at the energy transition market. So we will very much be focusing on some of the subtleties in some of the other products that we have and how they're really quite focused towards things like energy transition of battery storage, whether it be waste recycling facilities, wind turbines, etc. So thank you very much, everyone. There will be the survey sent out, and it is completely anonymous, just so everyone knows. So please be honest. The feedback will make these webinars better, and we hope that you found them valuable.
All right, thank you. Yeah, finally, thank you very much, everybody, for attending the webinar, for signing up and spending I know everybody is very busy despite the lockdown. So thank you for your time, your appreciation, your input with the answers and the questions. And we will, as we did before, make a recording of this webinar available to you. We'll send some further information in the next few days. I wish you a safe rest of the day, safe Thursday. And yeah, we look forward to seeing you next time. Thank you, everybody.
Thank you.